Hello everyone, my name is C-Dubs. I recently graduated from high school. I took BC Calculus, and today we are going to be talking about limits, continuity, and differentiability. Woo! Just so you know, if you want more videos on this topic, there are a lot more videos on this channel, and if you want to do this worksheet along with me, or if you want to do it on your own, the worksheet will be linked in the description, so look for that. But anyway, let's get into it. Okay, so first question, what is the definition of continuity for a function? So the definition of continuity is that the limit, for example, the limit of the function at point x, that limit equals the function value. So it'll probably equal a number. And that's what we're showing right here. Right here, the limit as x is approaching a of the function x equals the function value itself. So basically what that means is what you're going towards is actually there. So if a were 0.1, like x equals 1, and you have a graph, then you're approaching 1, and then you actually do have the point x equals 1. Because there are instances in which you could be approaching it, but then there ends up being a hole, or the graph ends up not reaching that number. So continuity means you do actually reach that number. So basically another way of thinking of that is that if you're drawing a graph, you never lift up your pencil because it's continuous. So something we need to think about when we're talking about continuity is both sides. So if you have x and your a in the situation is 1, then you have to look at the graph approaching from the left side and from the right side because they might be going different ways. So right here, what we have here, this negative sign is implying the left side. So this is the graph from the left. And then right here, we have the limit from the right side. So basically, this right here is only a thing if these two are equal, because the left and the right have to both be approaching the same number, if that makes any sense. So this, the left side has to be approaching one number, and the right side has to be approaching the same number for it to be continuous. And then, once you know that both sides are approaching the same number, then you have to make sure that that same number is where the function itself is actually at. For example, the reason you have to have both is holes. That is a thing. So the left and the right could both be approaching the same number, and they could come together like this, but then right where they're about to meet, the point is somewhere else, and it's not continuous. So that's why you need to have both this. They need to be both approaching the same point, but then they have to equal the function itself so that we know that there's actually a point there. So always when you're talking about continuity, you have to equate the limit itself to the function. And a lot of times you have to separate left and right to get to the limit itself. Okay, next question. What is the relationship between continuity and differentiability? So this is the thing you need to remember. Keep this in mind. Differentiability implies continuity. So differentiability is basically when a derivative exists or there is a slope. So when something is differentiable, then you can take the derivative, which means there's a slope because the derivative is a slope. So differentiability implies continuity because if you have a slope at a point, then that actual graph has to be continuous. You have to have a point for there to be a slope. If there's no point, there's no slope. So if you have a derivative, then it's definitely continuous. But the other direction, as I'm writing right now, is not necessarily true. So continuity doesn't necessarily imply differentiability. So an example of this would be absolute value. So you have your absolute value, and it comes to a sharp point at the top, like right here. It's a sharp point. And at sharp points, there is no slope because it comes to a sharp point and they're going in opposite directions. So there's no slope for absolute values, but there is a point there, and when you're drawing it, you never lift up your pencil. So that point would be continuous, but since it's a sharp point, you can't take the derivative and there's no slope, which means it's not differentiable. So a function can be continuous and not be differentiable, but if the function is differentiable, then it is continuous. So differentiability implies continuity. All right. So number 3. Now this is a piecewise function right here. And piecewise functions are very common with these kinds of questions because it'll have a left side and a right side like we were talking about in number 1. So a lot of times the left side and the right side might be different. So they want to test you on that. Okay, so find the value of each limit or explain why the limit does not exist. So the first thing we're going to do right here, we're going to evaluate the limit. So we have to find the limit of each part. As says the question, sorry I'm taking so long to write it. So first we have this plus sign, and you would like to remember that the plus side means that we're talking about the right side of the function. So if we're talking about the right side, then we need to figure out which function we're using. And we know that we're going to use this function here because it's greater than. So right side, we want to do greater than. And you can think about this, plugging in a number. It's just anything from the right side. So if x is equal to 2, and you can think about it visually, like if you're looking at a graph, you're looking at number 2 and you want the right side of the graph. So you want something bigger than 2. So when it has the plus sign, that means we want the greater than on the piecewise function. So we identify that, and then we write it out. Write out that function that it goes with from the piecewise. And then going to plug in. So we have 2 is our number, so we plug 2 into x. 2 divided by 2 is 1. 1 minus 1/2 is 1/2. So there's our value for the right side of the function's limit. And then we have the left side. So the left side, we see the less than. So we use this. We plug in our 2. -2 plus 3 is 1. So then you want to notice that these two numbers are not the same. 1/2 and 1 do not equal each other. So then we know that the limit going to just 2, the limit approaching 2, does not exist because these two numbers are not the same. And as we talked about in the beginning, the definition of continuity, the left side of the function and the right side of the function have to be approaching the same number. They have to be equal. And since they are not equal, well, okay, sorry, I misspoke. They are both approaching the same function. That's what this whole thing is. The same number. They're approaching the same number. That's why this is approaching 2 from the right, approaching 2 from the left. So they're both approaching the same number, but they have to be equal. Sorry. The two limits have to be equal, and since the limit on the right side is not equal to the limit on the left side, then the limit as a whole does not exist. So then we have a limit to, we have a different number. So this is not the number here. Well, okay, what we would call this right here is the split point. This number where the 2, and we're splitting into the left side of the function, the right side of the function. So 2 would be the split point here. 0 is not the split point. So there we just want to look at greater than or less than. Since 0 is less than 2, we use this, and we get 1 again. Sorry, not 1, because we're plugging in 0. My bad. 3, because -0 plus 3 is 3. Nice, okay. Sorry about that. All right, nice. Okay. Also, just to clarify, when we're talking about left and right side, just in case I haven't explained it well enough or made it easy to visualize, when we're talking about the function from the right, we're basically getting closer and closer to 2. So the point of this is that we're as close to possible as 2 as we can be without actually being 2. So here we're plugging in numbers greater than 2, and then we're getting closer and closer to 2. So 3.5, 3, 2.5, 2.1, 2.01, 2.0001. So we're getting closer and closer and closer to 2. So that's what approaching. Okay. And same thing from the left side. So from the left side, it would be less than 2. So it would be like 1, 1.5, 1.9, 1.99999. So approaching closer and closer to that split point. Okay, cool. Nice. Number 4. Yeah, let's go. Cool, cool. All right. Nice. Moving that page so it's easier to see. Okay, so this is another piecewise function. And this time we're finding the value of the constant c that makes the function continuous. So here we see our piecewise function, we see this variable. Well, I guess x is the variable, c is a constant, but we want to find c. So what we're going to do is we're going to look at our left side of the function. We're going to look at the limit for the left side, and we're going to look at the limit for the right side, and then we're going to look for the limit overall, and then we're going to look at the function. So it's kind of several steps. So the first step we want to do, we're looking at the left side of the function. So left side, if you remember, we want to look for less than. So that less than would be x is less than 5, so then we would write down the function that correlates with that. If my hand weren't covering the screen. Okay. And then for the right side, you want to look for the greater than, and you want to write that down. My hand is still covering it. I am sorry. Okay, nice. Okay, we got a nice little shot. Okay, so the less than, we put this over here. And we're looking at the limit. We're plugging in 5 because that's our split point. So we plug in 5. 5 squared is 25. 25 minus c. So that's our simplified version, and we want to keep that, and then we'll use that in a second. So for the right side, we plugged in the greater than part of the piecewise function. We put it here, 4x plus 2c. And then we plug in our split point. That's plugging it in, 20 plus 2c. Cool. So now we have these two parts. And then if we remember from the beginning, we need the left side to be equal to the right side. So we're keeping that in mind for in a second, we'll use that. Right here, we're writing the function itself. And what we're going to do when we're writing just the function is we're going to do the part of the piecewise that is equal to. So since this part has the equal to, we're using that, and that'll be the same as the left or right side. In this case, it's the right side, but it'll be the same of whichever one is the equals part. Oh wow, my finger just sticking out right there. Okay. So now, because we know that the left limit has to equal the right limit, we are going to set this, what we got here, equal to this here, so that we can find c. I do be taking my sweet time to write this stuff. Okay, so that's what we're doing now. We're setting them equal to each other. And so 25 minus 25. 5 equals 3c. Is that what it is? I can't see it. I'm sorry. 5 equals 3c. Oh, okay. Hold on 1 second. I gotta switch videos because my phone ran out of storage. Okay, cool. We're back. And there we go. 5 equals 3c. C equals... That is definitely wrong. So 5 divided by 3 is 5/3, not 3/5. So sorry about that mistake there. But c equals 5/3, not 3/5. So cool. Okay, nice. And then right here, we're gonna write our sentence. So this is the sentence you'll write for any of these problems, and it's pretty like formulaic, the sentences, so it's pretty easy to write for each one, as long as you know your numbers and as long as you know the numbers that you've literally just created for the answer. Anyway, so if c equals 5/3, then f of x is continuous at x equals 5, because the limit as x approaches 5 is equal to f of 5. And that's the definition of continuous that we had at the beginning, if you remember. So the limit as x approaches whatever is equal to the function at that number. And here we proved it. Nice. Okay, so now, number 5. Now we have a constant a instead of c. Changing it up. So again, piecewise functions, very common. So we're gonna, as we said before, we're gonna do our steps. The first step, we're doing the left limit. So here we have the left limit. -1 is our split point. So we wrote it here, we rewrote it. And then we're plugging in -1. So we have -a plus cosine of -pi. And then I think we're gonna simplify it one step more and do the, we'll just sub in what cosine of -pi is, because that is a number that we know. So cosine of -pi, if you know your unit circle, is -1. So we've simplified that as much as we can. Always be good to simplify as much as you can. And then we'll do the right side. So the right side, again, we want to choose the one that has the greater than for the right and the less than for the left. So for the right, we're going to be using this one and this function. We're plugging in -1, 1 plus 3a. So we have our left side and our right side. And then, you can't really see, but I guess I'll probably scroll down in a second. But what I was drawing and what you can't see is that, like we did in this problem, I wrote the function. So I did f of -1, and then I wrote the function that was the equal to, well, not equal to, but partly equal to, the less than or equal to, and equal to. Okay, anyway. So I also wrote the equal to down here. So the equals to was this one. So I had f of -1 is equal to this. And then since we already did the work of simplifying, I just copied down the simplified version. Okay, now, again, we want to make sure our left limit is equal to our right limit. So we're setting these equal to each other, and we're solving for a. So -1 minus 1 equals 1 plus 3a, -2 equals 4a, a equals -1/2. And yay, we did the dividing correctly this time. Yay. And then we're going to write our sentence. So our sentence, if a equals -1/2, then f of x is continuous at x equals 1, because the limit as x is approaching -1 equals f of -1. So you can kind of see this formulaic sentence, so you can kind of just memorize it and use it for the future. Just plugging in, this is your constant and your value that you found for the constant, split point, and then we have, oh, you can't see, split point, and then the limit is equal to the function. And remember that the definition of continuous is that the limit as x is approaching a equals the function at a. So that is the thing that you always want to put in your sentence, and that is what you need in your sentence. You don't need the left is equal to the right side. You need the limit is equal to the function. Make sure you have the function part in there. Very important. Okay, number 6. So we've got another little piecewise here. This time, quite a large function there. And if you'll notice here, what we've been doing before this part is we've had some less thans and greater thans, but this time we have an equal to and a not equal to, and that means that this is an absolute value question. And even if it's presented in a different way, so this isn't how we normally see it, we normally see it looking like this, but in this time it's equal and not equal to, but just always remember that you're doing the steps of doing the left limit, then the right limit, and then the function, and then setting them equal and writing your sentence. So, the left side of the function. I guess we'll, there we go. Oh, my hand has come out. Let's see. Am I gonna write? There we go. Okay, so we're gonna do the left limit. So the limit from the left, basically for this one, the left limit and the right limit are going to be the same since we have equal and not equal, because the point is that we're doing what doesn't equal 1 because we're doing what approaches 1. So we don't want it to be equal to 1, we want it to be approaching 1 for the limits when we're doing approaching left and right. So when it's not equal to 1, that is on the left side and the right side of 1. So this is going to be what we're going to use for the left side and for the right side. But I will write it twice because we want to do those steps. So this is the left side, we wrote the function. But then if we plug in 1, it is it doesn't work out. It's 0 over 0 because 1 minus 3 plus 2 is 0. And then 1 minus 1 is 0. So 0 over 0 means we have to do L'Hopital's rule. And if you don't know what that is, you can look. There are other videos on this channel that have L'Hopital's rule, but that's what we're going to do since we can't have a 0 over 0. We have to have a legit number. So this is going to be me doing L'Hopital's rule, which basically means we're going to take the derivative of the top and then the derivative of the bottom. So the derivative of the top would be 3x squared minus 6x plus 2 over 1. And then from there, I'm going to plug in 1 again. Sorry. So this is going to be me taking the derivative. And just so you know, sometimes when you take the derivative and you do L'Hopital's rule, it may not work. You need to make sure you plug in 1 and get a real number and not 0 over 0 again, because sometimes you might get 0 over 0 again and you'll need to do L'Hopital's rule again. But we plugged in 1 and we got, let's see, 3 minus 6 plus 2 is negative 1. And then here for the function, that's when we use the equals. So for the left and right, we use the not equal. For the function itself, we use the equals, and that's just c, so we have that here. And since we would be setting these equal to this, we do c equals negative 1, because we had negative 1 here. And there we go. We got our c. And then, again, you'll need to write your sentence. So your sentence is going to be if c equals negative 1. So again, that formula of if constant equals number, then the function is continuous at split point at x equals 1, because the limit as x is approaching, fill in the blank, in this case it's 1, the limit as x approaches 1 of the function equals the function, f of 1. So there you go, you have your sentence there. Nice. All right, number 7. Show that the following function does not have a derivative at x equals 1. Show that the function does not have a derivative at x equals 1. Okay, so does not have a derivative. So if you see the word derivative, then you think differentiability. And then we're still going to do the same steps that we did before. So we do the left side, the right side, and then the function itself. So here we're doing the left side. And the left side, we're looking at the less than side, so x squared plus x. We plug in 1 because that's our split point, so 1 plus 1 is 2. And then we do the right side, we do greater than, we use that, we plug in 1, 3 minus 2 is 1. So we have our left side and our right side. And then in this case, the sentence is going to be different just because the question is different. So the reason that we're looking at continuity is because we know that relationship between differentiability and continuity. So when you see a derivative, you think differentiable. And then you think differentiability implies continuity. So if we want to figure out how the function does not have a derivative, then we need to show that the function is not differentiable. And if it's not differentiable, then it can't be continuous. So in this case, since we have here the setup for continuity, then we want to show that the derivative is not continuous. So Actually, I think that a function can be continuous and not have a derivative. But, okay, so let me rephrase. A way. So differentiability, you have to have several things for a function to be differentiable, and continuity is one of those things that a function has to have to be differentiable, but it has to have all three things. So if it doesn't have one thing, like continuity, then it can't be differentiable. So if we show that the function is not continuous, then that means that the function is not differentiable. So that's, okay, that's a better way. If it's not continuous, then it's not differentiable. So since we know how to show continuity, or we know how to show that it's not continuous, that's why we're doing it here. That was a lot. I'm sorry about that. But if it's not continuous, it's not differentiable. So that's what we're doing here. So our left side is 2 and our right side is 1. If 2 doesn't equal 1, as we said at the beginning, the left side and the right side have to be equal. So since we showed that they are not equal, then that means the function is not continuous, which means the function does not have a derivative. So the sentence here is a little different just because we're proving something different. We're proving that it's not continuous instead of proving that it is continuous. So 2 does not equal 1. So the function is not continuous at x equals 1. The function is therefore not differentiable at x equals 1. Cool. All right. Nice. Cool, cool, cool. Number 8. Find the unique values for a and b that will make the following function both continuous and differentiable. So we know how to make it continuous. So this problem itself is a bit longer, and the other problem is also longer. They're kind of the same problem. So we're gonna talk about the steps. So since this problem is a little extra long, there are a couple of steps. So what you're gonna start out with, just so you know, we'll have several equations that we're going to be working with in this problem. So we're starting out with plugging in x, and because this question is so long, we're going to be simplifying it when we're doing it, just so that it's a little easier. In our other problems, we were very, shall I say, descriptive, very, I don't know, yeah, sure, we'll go descriptive. When we did our left side and our right side, and then we did the function itself, when we did that, we wrote it out very well and very clearly. We wrote it out very clearly, the limit as x goes to whatever. But in this case, since we're going to have multiple equations that we're using, we're just going to kind of go for it instead of writing the whole left-right function. So basically, we're just going to be doing the left and right and setting them equal to each other, except we're just doing it in one go instead of writing out all those steps. But you can write out those steps if that makes it easier for you, and if that's easier to understand, because it is easier to understand that way. So what we did here, we plugged in our 1. So we have what would be our left side, our less than would be this. This would be our 3 minus x. And then we plug in our 1. So 3 minus 1 is 2. So we have our left side. And then our right side, greater than a, it would be this whole thing. And then we're plugging in 1. So a plus b. So we did our left side, we did our right side, we set them equal. So that's what we did here. We just did it in one very succinct step. And then the next step is we're going to take the derivative of both sides from our nice simplified equation. So the derivative of 2 is, I don't know, it's not really that. You know, okay, I just said derivative of 2. I didn't mean derivative of 2. I meant derivative of this. So when I say derivative of both sides, not the derivative of the simplified thing that we just wrote. It is the derivative of the function itself. Sorry, that was a little confusing. So the derivative of this function is -1. The derivative of this is 2 times a times x plus b. So we wrote that out, and now we're going to plug x equals 1 into that derivative. So we plug it into x, so this is the equation we have now. So this is our first equation, this simplified, so if you ignore the 3 minus 1, but it's just 2 equals a plus b. And then we have our second equation here. And now we're going to do kind of a systems of equations. And you can do this however you see fit in the problem. You can add the equations, subtract the equations. If you want to use substitution, you can do that. What we did in this problem is we just subtracted them. So we did 2 minus -1, which is like 2 plus 1. 2 plus 1 is 3. And then we subtracted this side. So a minus 2a is negative a. B minus b, 0. And we did that so that we could isolate one of the variables and set it equal to a number. So we have a equals -3. And then from that, we get to plug it back in. So we have -3 times 2 is -6. Add it to this side. 6 minus 1 is 5. B equals 5. So that is how we find our 2 unique values that the question is wanting. And since that's all the question was asking for, you don't have to do anything else. You don't have to write another sentence. Yeah. Since it's only asking for those unique values and not asking like why something is continuous or something like that, since it's just asking for the values, that's why we can do the whole simplified version of the left side, the right side, the function, taking the derivative. That's why this is kind of a more Cliff Notes-y version. Okay, so it's the same question as before, different setup. So we're going to do our first step, which is doing the left-right function, or just left and right, equating the left and the right sides. And we're doing that very succinctly. So we want to look at, oh, this is the left side because it's less than, and we're plugging in 0. So a minus 0 plus b times e to the -0. And e to the 0 is just 1. So that would be a minus 0 plus b. So we're just going to have a plus b. So that is the left side. And then we want to look at the right side. So it's the greater than side. So we're looking at this, and then we're going to plug in 0. So a times sine of 0. And sine of 0 is 0. So basically this is going to be 0 plus, and then we're plugging in nothing because b is just a constant. So this is 0 plus 2b. So it's just 2b. So we have that part, and then we're going to take the derivative of the original equations. So if we're taking a derivative of this left side, a is a constant, so a goes away, minus 3 plus b times e to the -x times -1, because we're doing that chain rule. And so the negative would be here. So we would have -3 minus b times e to the -x. And then the right side, wait, did I already say the right side? No, I didn't, right? Okay. So we're doing the derivative here. So we want to look at the derivative of sine as cosine. So cosine of pi x times a. And then times pi, because we want to do that chain rule again. So we have a times pi times cosine of pi x. And then b, again, is a constant, so that goes away. Always keep in mind when you're taking the derivative, it gets a little confusing sometimes, but you have to remember that the a and the b, or whatever constant they use, they might use different letters, that those are constants and not variables, so you don't take the derivative like x, you take a derivative like it's a number. Okay, and then we're plugging in our x equals 0 into the derivative, so -3 minus b equals a times pi. And sorry I didn't cover this, but right here I just simplified it so that when we do the actual equation stuff, it'll be easier. In this case, we'll probably substitute because we already have a equals b, so that's pretty easy. But we subtracted b here, a equals b. So now, again, we have our 2 equations. So this is our first equation, and this is our second equation. So we're going to then do a systems of equations. In this scenario, we will do substitution because it will make the problem a lot easier just because a equals b. So we can just plug in A into B, and then solve for A. And that's what we're doing here. And we'll solve for A. Cool. And then here we just took out A, so A times pi plus 1 and then divided. And then since this is our A, we plug A in. Or no, you don't plug A in anywhere. We saw here that A equals B. So we already know that this equals this. Okay, sorry. Nice. Okay. If they weren't equal to each other, you would plug A back in, but they're equal to each other. So I guess you are plugging them back in, but anyway. Okay. Yay, we finished the worksheet. Woo! Okay, good job. That was a little rough, but we got through it. Okay. Just good job. This was limits, continuity, and differentiability. If you want more videos of that, of each individual topic, we have those on this channel. If you liked it, feel free to subscribe and like. You do whatever you want. Thank you for watching this video. Hope you learned a little something. I am C-Dubs. Goodbye.